Welcome to our third learning workshop over ionic and covalent bonding and naming and writing of formulas and all that good stuff. Um, well, let's go ahead and dive into this, shall we? Okay, so first of all, what are ions? You probably already know. I brought this fun little cartoon for you uh, regarding ion formation. Lost an electron. Are you positive? Oh, ho, 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 ho. It's like a good English joke without the good part. Ions refer to any particle that is either a positive or a negative charge. So ions are just any particle. Notice I say particle and not atom. Um, the particle can be a molecule, a charged molecule, or it can be a single atom. And if it is a charged molecule, we call these polyatomic ions. So if an atom gains an electron, it gains a negative charge, and therefore it becomes negative. If it loses an electron, it becomes positively charged. If you lose, let's say you're a negative person, if you lose your negative attitude, you become a positive person, right? So that's one way to think of it. It kind of helps. I don't know. All right, so how ions are formed. So the diagram below shows the transfer of an electron. So electrons are not lost or gained by themselves, so to speak. An atom just doesn't spontaneously decide to lose an electron typically. What happens is that there's a transfer of electrons from one atom to another. For example, the sodium ion gives up its electron to the chlorine ion here. So when atoms get close enough to bond, some have a greater attraction for electrons than others. This attraction is called electronegativity, as it mentions here. Atoms that are nonmetals, atoms that are further to the right on the periodic table, up and to the right, though they have greater electronegativity, and therefore they are more likely to take electrons, and atoms that are further down are more likely to give electrons up. So like the pattern for electronegativity is electronegativity increases going up, increases going to the right. And you'll notice that's also why you have nonmetals over here. Nonmetals tend to have very high electronegativities, and metals tend to have very low electronegativity. So the metals tend to be down here, nonmetals tend to be up here. And there's sort of a dividing line between them that we like to call, it kind of looks like a staircase. It's kind of like, do, 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 do. I'm sure you've seen that, right? But that's kind of how it works. Now, if two atoms have a very large difference in electronegativity, like one is a nonmetal, the other is a metal, then the atom that has a much greater electronegativity will completely take away the electron from the atom that has less electronegativity. And obviously that causes the atom that loses electrons to be positive, and we call positive ions like cations, and atom that gains electrons are called anions. So there's a really cool video I want to show you. All right.
Most atoms don't ride solo. Instead, they bond with other atoms. Now, bonds can form between atoms of the same element, or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice. in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now, these transactions aren't always so cut and dried. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus, and the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond, nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they'd better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
So that was yeah, I thought that video was really cool. I really enjoy it because it really gives a clear understanding of where these what's actually happening. What do you see on the molecular level? So let's do a little comparison between ionic compounds and molecular compounds. We can compare them. One good way to differentiate them is to ask a few questions about them. Okay. So, like for example, first of all, what happens to the electrons? For ionic compounds, what happens to the electrons? What do you think? Based on what you just saw. All right, excellent. Yes, absolutely. Good job, Frank. Ionic compounds give and take electrons. So some of the electrons are completely given by some atoms, and they're completely taken away by others. What happens to electrons in molecular compounds? They share. Exactly. Perfect. So one or more electrons from one atom is given to a different atom in ion compounds, and then they share in molecular compounds. In both cases, it's the valence electron. So then how does this affect the atoms? This is kind of a strange wording on this one, but basically, for ionic compounds, the atom that loses electrons becomes positively charged. The atom that gains electrons becomes negatively charged. But for molecular compounds, the two nuclei of the atoms are each pulling the shared electrons in a sort of tug-of-war fashion. They're both sharing them. They're both pulling on them, and that holds these two atoms together. It binds them together in what's known as a covalent bond. Neither atom is willing to let the electrons go, so it's kind of like this continual struggle. They're both kind of holding on to those electrons. So why do atoms gain or lose electrons? This is an important question. It's not asked often enough. Why do atoms gain or lose electrons? Or why do they share electrons?
Are they trying to become stable?
Yes, they're trying to become stable. Um, exactly. So The and the way that they become stable is it turns out that there are some atoms that have really stable electron configurations, that having a certain number of electrons makes atoms much more stable. Um, they're trying to become stable, and the most stable atoms that there are the noble gases. It turns out that having those numbers of electrons make it turns out that having that number of electrons is particularly stable. So if it can have 2 electrons like helium, or 10 electrons like neon, or um, or if it can have 18 electrons like argon, then it will be much more stable than the counterparts. Okay, so here's the deal. If the reason why these atoms, the noble gases, are more stable is something referred to as having an octet, or the octet. The turns out that it's much more stable if you have 8 electrons in your outermost shell, and each one of the noble gases have 8 electrons in their outermost shell. So each atom will end up trying to gain or lose electrons to get 8 valence electrons in its outer shell, and that's known as the octet rule. Okay, so what does this bonding look like? Well, we kind of have a little bit of an idea from the previous video. Oppositely charged ions stick together like magnets in a continuous 3D pattern called a lattice. By now you've seen a few different images of that. Kind of cool. For covalent compounds, each group of bonded atoms is a separate, distinct molecule that has a definitive beginning and a definitive end, whereas ionic compounds don't have a definitive beginning and a definitive end. The quote-unquote molecules, or the pieces of an ionic compound, can vary in size dramatically, because as long as there's more positive ions and more negative ions, the crystal will just keep getting larger and larger. Okay, so I want to show you another cool little video. This is a very short video, but I think it's worth watching.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions, and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
Cool. So just a kind of a fun fact here. If an atom was the size of or if the nucleus was the size of a basketball, how big would the atom be? Any guesses? The nucleus was the size of a basketball, how big would the atom be? This is a fun guess. Just you don't have to actually know it. Just what do you think? Twice as big. Okay. Any other guesses? The nucleus is the size of a basketball. How big it would be? How big would the atom be? Got only one guess. Only one brave soul comes forth to guess. Yards? Okay. Anybody else? Anybody else want to venture a guess? Okay. All right. I'll tell you the facts. I'm sharing facts here. If the nucleus is the size of a basketball, the atom is the size of Texas Stadium. Think about that. The nucleus is the size of a basketball. The atom is the size of Texas Stadium. Yeah, the entire stadium, the entire thing, including the atrium. Yeah, the nucleus is actually a very, very, very small part of the atom. Most of the atom is composed of empty space. The electrons fly around the nucleus um, quite far away from the nucleus, but they're very strongly attracted to it. And most of the size of the atom is that electron cloud. Yeah, pretty crazy, right? So, if that's the case, why don't we just like phase through each other? Since most of atom is like empty space, why can't we just like walk through walls or something like that? Well, it turns out it has to do with electrostatic repulsion. The electrons are spinning around at literally about 1/100th the speed of light. So basically, hundreds of thousands of miles per hour, those electrons are spinning around the nucleus. It's ridiculously fast. So it creates kind of like a shield, a force field, so to speak, that when the electrons from when an electron from the outer surface of your hand come into contact with the electrons from the outer surface of someone else's hand, those electrons repel one another, and that's why you can't just phase through something, even though the atoms are made up of mostly empty space. Pretty interesting, huh? Okay, so let's dive into this. And that's actually an important point. The reason I bring that up, because that also explains why only the outermost electrons are involved in bonding. So here we go. This is a picture of a sodium chloride lattice. It's kind of a model, and we can't really describe sodium or ionic compounds as forming molecules because of that, because they have no definitive beginning or end. It's just a continuous array of positive and negative charges. And so therefore, we refer to the smallest empirical formula unit, the smallest repeatable unit, as a formula unit. And that's essentially the empirical formula for the compound. So we just say NaCl. It's not a molecule, but it's a formula unit. When we do our mole conversions next week, that'll be that's why we will convert from grams of sodium chloride to formula units instead of grams to molecules. Here's another image of the crystal. So let's look at writing formulas for ionic compounds. One of the trickiest things for writing formulas for ionic compounds is being able to figure out what their charges are. So this is a little excerpt from an image of the periodic table that shows how you can find the charges. Let me want to go through why these charges are the way they are. Okay, so let's take a look at this. So you'll notice that noble gases, that's these guys right here, they're very happy. They do not form any charges and they don't react with anything either because they have just the right amount of electrons. So but if I look at an element like fluorine here, fluorine is very close to neon. It has almost the right, it almost has a stable number of electrons. It really wants 10 electrons, but it only has 9. So because it only has 9 electrons, it's going to gain an electron to be like neon. And if it gains 1 electron, it becomes a -1 charge. What about oxygen? So oxygen has 8 electrons. How many electrons would oxygen gain if it wants to be stable? How many electrons would oxygen gain if it wants to be stable? 2, yeah, it gains 2 electrons because it has 8, it wants to be like neon, that's 10. So it's going to gain 2 electrons and it's going to become a -2 charge. Very good. And then nitrogen, as you can see, has 7 electrons, and therefore it's going to need to gain 3 to be like neon, and it'll be a -3 charge. But what about carbon? Carbon's right here. Carbon's right here. It has 6 electrons and 6 protons. So carbon is actually, it could either gain 4 to be like neon, or it could lose 4 and be like helium. What do you think carbon's going to do? Gain 4 electrons? Yes, Frank, what do you think?
Depends what's easier. I mean, depends on the what's sharing with it.
Yeah, so in truth, shame on me, that's a trick question. You're right, it depends on what's easier, but the truth is neither one is easy. It's not easy to gain 4 electrons and it's not easy to lose 4 electrons. While it's true that carbon on rare cases can gain 4 electrons, generally speaking, carbon does not form an ion. It's just too hard to gain or lose electrons. It's like, nah, it's too hard. I'm not going to do it. It's kind of like us, honestly. At some point, if something is so ridiculously hard, we're like, nah, I'm not going to do it. I mean, if we could all like make a bunch of money by like, doing something really easy, we'd probably do it. But if it's really, really, really hard, and you're like, nah, I'll pass. And that's kind of like what carbon does. So if we look at aluminum, however, aluminum has 13. It could gain 5 to be like argon, or it could lose 3. Which is it going to do? Is aluminum going to gain 5 electrons to be like argon? Or is it going to lose 3 electrons to be like neon? Yeah, absolutely. It's going to lose 3. It's going to lose 3. So aluminum's going to be a +3 charge. So the atoms are all trying to gain or lose electrons to be like the closest noble gas. They're going to do whatever is easiest. And in this case, aluminum's going to be +3. Now, you'll notice that this big blue section here, encompasses all these elements. These elements here are referred to as transition elements because they can have multiple charges, okay? And because they can have multiple charges, there's no way to predict what their charge is going to be by looking at the periodic table. So instead, we have to figure it out from in other ways. However, there is this nice, neat little exception, shall we say. And that is, I refer to it as the magic staircase, okay? And the magic staircase is this thing right here. And I unfortunately think you are going to have to memorize this. Most professors do make you memorize this, but Silver is always a +1. Zinc and cadmium are always a +2. And gallium, aluminum, and indium are always a +3. Technically indium might on some rare occasions be able to be a +1, but we're going to say it's always a +3 because that's all you're going to ever have to deal with it. So aluminum, gallium, so there's 3 +3s, 2 +2s, 1 +1. Remember the magic staircase. Everything else outside of the magic staircase, there's no way you can predict it unless it's a non-metal, unless it's one of these guys over here. These are predictable. Or if it's one of these guys over here, these are predictable. But the middle ones, those are not easily predictable. Only the magic staircase you unfortunately have to memorize. So for the writing formulas for ionic compounds, the first thing we do is determine what the ions are along with their charges. Polyatomic ions, once again, you're just going to have to memorize because there's no clear repeatable pattern. Some professors might be nice and allow you to use a list of polyatomic ions. Other professors make you memorize them. So, and I'll tell you, the most common polyatomic ions, the most important ones, the big 8, so to speak, I'll actually write those down here, and you should write them down on your sheet and work to memorize them with flashcards or whatever. If you know these 8, you're going to be in good shape better than 90 to 95% of the time. Almost always, whenever I've seen questions with polyatomic ions show up on a exam, it's always one of these 8. So there's ammonium, which is the only positively charged polyatomic ion. The only positively charged polyatomic ion is ammonium. And then there is nitrate, there's chlorate, there is acetate, U2, H3, O2. This is called acetate, ACE. You can get this from vinegar, acetate. Don't know why I drew that big line there. Hydroxide, OH minus. This is a very important one, hydroxide. Then there is carbonate, CO3, Q minus. And then there's sulfate, SO4, Q minus. SO4, Q minus, sulfate. And then there is phosphate, PO4, 3 minus. So these are the big 8. These are the most important polyatomic ions. The ones that show up the most often, the most common polyatomic ions. Ammonium, nitrate, chlorate, acetate, hydroxide, carbonate, sulfate, and phosphate. I apologize if my writing is a little bit hard to read. I hope that's readable. Okay. You all got that copied down? We good to go? All right, let's dive into this then. So, it, so the next step is find the lowest common multiple of the two charges. The lowest common multiple, or LCM. So the key thing to recognize is that with an ionic compound, the total number of positive charges must be equal to the total number of negative charges. So to determine how many of each atom must be present in an ionic formula, we need to look at the lowest common multiple. So let's say, for example, we have magnesium phosphate. Well, magnesium from the periodic table we know is a 2+ charge. Phosphate is one of those polyatomic ions we have to memorize. It has a 3- charge. So the lowest common multiple, remember multiples are like counting by that number, so multiples of 2 counting by 2s, 2, 4, 6, 8, 10, 12, etc. Multiples of 3 would be like 3, 6, 9, 12, etc. So the lowest common multiple of 2 and 3 is 6. That's the one that they both have in common. 2 is only a multiple of 2, not a multiple of 3. 3 is not a multiple of 2, but the one that they have in common, the lowest common multiple, is 6. So then notice this is the second multiple of 3, and this is the third multiple of 2, which means I need 3 magnesiums and 2 phosphates. So we figure out how many cations I need to get to the lowest common multiple. I need 3 magnesiums to get a total charge of 6. I need 2 phosphates to get a total negative charge of 6. And then I can write the formula. I put an Mg, and I indicate the number of magnesiums with a subscript 3. Now, since I need more than one polyatomic ion, I have to use parentheses. So I'll do PO4, close parentheses, 2. Think of it as doubling the recipe. I have to put parentheses around it because I have to indicate that I need 2 of the whole thing. I have to double the whole recipe. So Mg3PO4 2. And that's basically what I just said. You write the and positive ions always go first. Metals always go first. That's just a side note here. Metals always go first. Negatively charged ions always go last. So metals first, and then non-metals or negatively charged ions last. So let's do some practice. Write the chemical formula for the following compounds. We'll do the first one together, and then I'll leave you guys to do the next two. So calcium has what charge? What's the ion symbol for calcium? What do you think?
Ca2+.
Yep, Ca2+. So I'll do Ca2+. What's the ion symbol for bromide?
Br.
Br with a
Minor.
-1 charge. Very good. So lowest common multiple of 2 and 1 is 2, right? Because multiples of 2 are 2, 4, 6. Multiples of 1 would be 1, 2, 3. The lowest common multiple, etc. Lowest common multiple would be 2. So I need 1 calcium and 2 bromines. So 1 calcium gives me a 2+ charge. 2 bromines gives me a 2- charge. And I get CaBr2. Does that make sense?
I didn't get that really.
So basically, I'm trying to get the total positive charges to equal the total negative charges. Calcium's a 2+, bromine's a -1, So the multiple, like the lowest, but what the lowest common multiple of 2 and 1 is 2, because multiples of 2 would be like 2, 4, 6. Multiples of 1 would be 1, 2, 3. So the lowest common multiple is 2. How many calciums do you need to get a total charge of plus 2?
I think what the goal is here is to be able to see how both sides can balance up to be equal to 0, right?
Both sides have, yeah, balance the charge of both sides. That's right. That is correct. So there's multiple different ways of doing that. The lowest common multiple way is just the way that I was showing. Some professors like to also show like what's known as the crisscross method. They'll go like this. We'll just use that as a subscript here, use that as a subscript there. The only problem with the crisscross method is it doesn't always work. And it also leads to conceptual confusion. That's why I don't like the crisscross method and I don't encourage it. But you can use it, just be very careful because it can give you the wrong answer sometimes. All right. So I'll give you some examples of that later on. Okay, let's go ahead and take a shot at B and C. Go ahead and figure out what what those are. And once you have an answer, just go ahead and hit the little raise hand button when you have an answer for the last two.
I'm not sure what is it Al3 plus 02 minus? I'm not sure.
No, that wouldn't be the formula for it.
Oh, that's the formula.
What do y'all think? Do you want to go over it? You want to go over these two together?
I think so.
Okay, no problem. Okay, so the first thing we're going to do is we're going to look for the charges of each one of these. So aluminum is and actually let me change my color here. I'm going to actually use this one. Aluminum is a 3+ charge. And you can tell it's part of the magic staircase, right? You could also kind of predict in the fact that it has 13 electrons and it wants to be like the closest noble gas, neon. Oxygen, oxide, is oxygen, and that has a 2- charge. So now I have my ions. The lowest common multiple of 3 and 2 is what?
6.
6, exactly. So since the lowest common multiple is 6, how many aluminums do I need to get a total charge of 6?
2
Exactly.
and 3.
So 2 aluminums, so I'll put Al and then I'll put a little subscript 2. The subscripts tell you how many that you have, and the superscripts tell you the charge. So they tell you two very different things. And the oxygen, I need 3 of them, as you mentioned, to get a total of 6. 3 times -2 is -6. So this would be my aluminum oxide.
Oh, I get it now. Okay.
So let's do zinc nitrate.
Can I ask a question?
No. No, I'm just kidding. Yes, you can.
Sorry. So what I want to understand now is that when you're trying to get your formula, you the multiple that is missing, right, is what finally becomes your answer, right?
Well, you're looking for the lowest common multiple because that will tell you how many of each you need. That'll help you figure out how many of each ion you need to get a balanced compound. Yeah.
Yeah, I got it now. It makes
Okay,
sense.
cool. So let's take
Thank
a
you.
look at, no problem. Let's take a look at zinc nitrate. So what's the charge of zinc? What's the charge
Zn
of zinc?
minus.
Oh, not a minus. Yeah, very good, Frank.
Plus.
Yeah, 2+. This is one of those magic staircase elements. Zn2+. And Frank went ahead and shared with us. Zn2+. And then what's nitrate?
NO3 minus.
Yeah, it's NO3 minus. NO3 minus. So we have Zn2+ and NO3 minus. So what's the lowest common multiple of those charges? I got a -1 and a +2.
6.
Nope. The
No?
charge of nitrate is not 3. The charge of nitrate is a -1. There's 3 oxygens, so you got to be careful you don't confuse Yeah, you don't want to confuse the subscripts for superscripts. The superscript tells you the charge, and the charge of nitrate is -1. So yes, as
Two.
yeah, it's
Two.
2, um, 2, 4, 6, and then like 1, 2, 3. Those are your multiples. The lowest common multiple would be the 2, as Frank mentioned and as you mentioned. So I need how many zincs then?
1 ZN.
1 ZN. And if I only need 1, I don't need to put a subscript 1. I don't need to put that
No,
1 there. So I'll get
no,
rid of that.
no.
And it's 1 is assumed if I don't put it. And then how many nitrates do I need?
2. NO3 2.
Exactly. So and because it's a polyatomic ion, I need to use, what do I need to use if I have more than one polyatomic ion?
A bracket.
What'd you say?
Did it? I don't know.
Frank went ahead and shared it. It's parentheses. Yeah, I have to use those parentheses. They're called parentheses, the little half circles. Yeah, I have to put parentheses around it. If I have more than one polyatomic ion, I have to put parentheses around it to indicate that I'm doubling both of those. That 2 means that I have 2 nitrogens and 2 times 3 or 6 oxygens, so 2 NO3s. So this is my answer for zinc nitrate.
So why did when you have the -1 on top before, how come you now have the this what do you call it, the subscript or whatever? Why is it now at the bottom and not at the top?
It's it's by convention that the superscripts, the little numbers up top, should represent the charge differential. So if there's more negatives, the overall negative charge or overall positive charge is always supposed to go on the top as a superscript. The subscripts, the numbers on bottom, tell you how many of the atom there are. It doesn't tell you anything about charge. Does that answer your question, or were you asking something else?
No, that's what I was asking. Just that the
Okay.
chemistry is a little bit hard.
Yeah. Unfortunately, a lot of times what you'll find is that a chemist had to come up with some sort of a systematic way of representing all these things. So they kind of made a bunch of rules, and it's not that it would have to have been that way. It's just that it ended up being that way because they felt like that made the most sense at the time. Um, I mean, if they had wanted to, they could have put the charges on bottom, and they could have put the number of atoms on top, but that's not what they did. The charges are always listed as superscripts, the numbers on top, and then the number of atoms of each type is those numbers go on the bottom. All right, cool. Let's take a look at some other stuff then. Guidelines for naming ionic compounds. So we just went over how to write the formula of an ionic compound, but if you want to write the name of a compound when you're given the formula, here's how you do it. First, you name the cation first. Generally speaking, that's a metal. Now, for a metal cation, it's just going to be named the same as the element. For example, aluminum 3 plus, if that's your cation, you're just going to call that aluminum. If the metal can have multiple charges, in other words, it's in that blue area that we talked about, if it's a transition metal, something like iron or chromium, you must indicate its charge with a Roman numeral because it can literally have a number of different charges. So for example, lead, Pb, can actually be a +2 or +4. So if you had Pb4 plus, you'd have to write it as lead and then put in parentheses a Roman numeral 4, lead 4, to indicate the name of the cation. Copper is another one that can have multiple charges. If it's a +1 charge, you would call it copper 1. So those Roman numerals tell you the charge of the transition metal. So after you name the cation, then you can name the anion, the negative ion. For a non-metal monatomic ion, or one-atom ion, the name of the anion is just the first syllable of the element, first syllable of the nonmetal followed by an IDE ending. So you'll notice that we came across oxide. Well, O2 minus is oxide. O is oxygen, but when it's negatively charged, we just use the first syllable and then give it an IDE ending. Likewise with chlorine, we use the first syllable, chlor, and then we give it an IDE ending. Phosphorus, we use the first syllable, phos, and then we give it an IDE ending. For polyatomic ions, there's no change in the name of the ion, so those are actually a little bit easier. As long as you know what the name of the polyatomic ion is, you can simply write that name. So let's take a look at how this works. Do some practice. And by the way, if I'm going a little bit too fast and you need me to slow down for a second, just let me know. I can definitely do that. So let's write the names of the compounds with the following chemical formulas. So for number 1, let's name the cation. What is the first, what's the cation called? What's the name of the metal ion for number 1?
Aluminum.
Aluminum. Or if you have some British influence, you might notice that in British English, aluminum is spelled differently.
Yeah.
In American English, we write it as aluminum. In British English, it's spelled aluminium, A-L-U-M-I-N-I-U-M. So aluminium or aluminum, depending upon if it's American or British spelling. And then we put the name of the polyatomic ion we have here. And what's that going to be?
Sulfide? No.
Sulfate. Yeah.
Sulfate?
Yes. Yes. Question.
Why do they spell sulfate this way? I'm used to spelling sulfate as S-U-L-P-H-A-T-E.
Once again, it goes back to British versus American spelling. Neither one is wrong. It's just a matter of a British versus American spelling.
Okay.
Yeah. It
So,
would be nice if we could keep our English straight. But unfortunately, we
but
it's quite different.
can I ask a question, Michael?
Yes.
Yeah, what's the difference? How do you know the difference between the sulfate, the sulfide, and there are some, I think there's a rule to
Oh,
knowing
are you
which
talking
is.
about are you saying sulfide, IDE, or are you saying sulfite, ITE?
No, I know there are three levels, right? You have sulfate, for instance, you have sulfite and sulfide. So
Ah,
how do we
yeah.
differentiate those three to bring in? Yeah, because I think when we know those rules, it's easier for us to just pinpoint what.
Sure. Okay, so here is yeah. Now I don't know if you're going to be expected to know. It depends on the professor. You may or may not be expected to know what the derivations of those 8 polyatomic ions are. I'm going to use chlorate as an example. Um, uh, I don't know why it keeps doing that to me.
Sorry.
No, it's okay. It draws these random lines, and I'm like, oh my goodness. So, but here's the chlorate. Okay, so here's the deal. Basically, if there are different oxyanion derivations, what that means is that sometimes an oxyanion can have more or less oxygens than you might expect. So if it has one less oxygen than the most common oxidation state, the most common oxidation state for a chlorate is chlorate, and it gets that ATE ending, and so that's the ClO3 minus. Okay, but if it has one less oxygen than than its most common oxidation state, then you would get an ITE ending, and it would be ClOR ITE.
TE. Mm-hmm.
So it's the same charge. It works exactly the same. The only difference between the 8 and the ite is that there's one less oxygen. That's the only difference. So same thing with sulfate and salt. Um, the only difference is there's one less oxygen. Uh, so then if you have, you can actually have even one less oxygen than that. You can have ClO minus. And if that's the case, you add a hypo in front of it. Hypo, and then it also has the chlorite, hypochlorite. So adding the hypo takes away another oxygen. So, and you can also have a situation where it has one more oxygen that's expected. Once again, the charge doesn't change. The charge is -1 for each one of these. But if it has one extra oxygen, then this would be referred to as perchlorate. So it has a per in front of it to indicate that it has an extra oxygen. Now, usually you won't have to deal with the per and the hypo, but a lot of times you will see the chlorate and chlorite, sulfate, sulfite, phosphate, phosphite. If it has an ITE ending, all it means is that you have one less oxygen.
Okay.
Cool?
Yes, cool. Thank you.
You're welcome. Now, so the first one is aluminum sulfate. What about the next one? Any ideas for number 2? What would that be?
Nitrogen. Hold on. NH.
Ammonium. Thank you for Frank. Frank says ammonium, and then something. Ammonium something. NH4 is ammonium. Very good. That's your polyatomic ion. It's one of your only positive polyatomic ions. So
NH4 is ammonium.
Yep.
Oh.
And then what's the S? If it's just a sulfur, but it's an ion, what's that called?
Sulfide.
Sulfide. Sulfide. I heard somebody say it. Sulfide. Ammonium sulfide.
I said sulfide, but I wasn't sure.
No, that's okay. That's good. Good. Your intuition's kicking in. All right. Yeah, it's sulfide. Sulfite would actually be SO. Sulfite would actually be SO4, or rather SO3. If it was ammonium sulfite, it would be like this. This NH, if I had NH4 to SO3, that would be ammonium sulfite. So, but that's not a bad guess, Myra. That's actually, oh, whoop, I don't know what I'm doing there. You'll actually find that that is common mistakes that a lot of students make. They confuse the sulfide with the sulfite. But if it has a T, it's a polyatomic ion. Sulfite. There's your sulfite. There we go. And what about the ZNO? What's that?
Zinc oxide. Zinc oxide.
Zinc oxide. Yep. No Roman numeral, right? No Roman numeral because it is one of those magic staircase elements. Zinc oxide. No Roman numeral. What about AgOH?
Silver oxide.
Silver. You're close. Silver what?
Hydrogen. OH is hydroxide.
Hydroxide. That's one of those polyatomic ions. Silver hydroxide. Silver hydroxide.
Did I get it?
You did. Silver hydroxide. There you go. Zinc oxide and silver hydroxide. Well done. That's exactly right.
I thought they said you can also call hydroxide bicarbonate. Is it that one?
Oh, no. You cannot call hydroxide bicarbonate. Bicarbonate is HCO3. HCO3 minus is called bicarbonate.
Yeah, that's true. HCO3. Yeah.
You can call it hydrogen carbonate or you can call it bicarbonate. But yeah.
Okay.
Hydroxide is not going to be called that. There we go. Now let's look at writing names. Now this is the most challenging part. Y'all got most of this down. This is the most challenging part that we're going to hit next.
think Jesse has a question.
Yep, Jesse, so if it is 8 or ite, it's going to be a polyatomic ion. Yep. And if it's IDE, it's an element. Yes, almost.
Oh,
There's only one exception, Jesse. Only one exception, and that's hydroxide. The OH, that IDE hydroxide, that's one of the only common polyatomic ions you have to worry about. Okay. There is cyanide as well, but you don't usually come across that. You won't. I'm pretty sure you're not going to see that. But yes, 8 and ite are always polyatomic ions. So if there's a T, always a polyatomic ion. If it's an IDE, it's almost always an element. The only exception would be if it's hydroxide. All right, cool. So, writing names for ionic compounds with transition metals. Here we have to follow a couple little steps. First, step 1 is calculate the total negative charge from all the anions. The only way to figure out the charge of a transition metal is to figure out the charge of what is bonded to it. And so we calculate the total negative charge from the anions, and we recognize that there is going to be an equal number or equal amount of positive charge. Then step 2, we divide the total positive charge by the number of transition metal ions. And then we can write the name of the compound, indicating the charge as of the transition metal with a Roman numeral. So let's go through those 3 steps here. I have SO4, 3. There's 3 sulfates, each one with a -2 charge. So that gives me a total -6 charge for the anions. If there's a -6 total charge for the anions, that means I have to have a +6 total charge for the cations. I know I have 2 irons here, so I'll take my +6 and then I will divide it by 2 to get a +3 charge per iron ion. From there, I can write the name of the compound. Since I know it's iron with a +3 charge, I'll call it iron 3 sulfate. Does that make sense?
I was thinking it was iron 2 sulfate because I saw 2 there just now.
Yeah, so you got to be careful about that because the Roman numeral doesn't tell you how many. The Roman numeral tells you the charge. The Roman numeral tells you the charge of the metal. And also, I know some of you are thinking this. You cannot do reverse crisscross. Okay? I know you're thinking, well, there's the 3. Yeah, that 3 tells you the charge of the iron, but that doesn't always work. And I'm going to show you some examples where it doesn't work. Yes, question.
Please, Michael, can you go back? I didn't get you well.
Oh, you want me to repeat what I just said?
Yes, please.
Oh, sure, no problem. I said, I know that some of you are thinking that you might be able to do this reverse crisscross thing where you basically take this 2 and you put it up there and say, well, that's the charge of sulfate, and you say this 3, well, that's the charge of the iron, and say, okay, well, then I know that the iron is a +3, and I can just write iron 3 sulfate. That's really dangerous because that does not work a significant amount of the time. You can't. I'll show you some examples for where that does not work, but you can't just reverse crisscross. That's a no-no. I'm gonna put in big letters. I'm gonna put no. Like no. Don't do that. Okay. So let's take a look. Let's write the names of the compounds with the following chemical formulas. So I'll go through the first one with you together, and then I'll have you do a few on your own, see how you do. Okay? So we have SO4 3. There's so Cr2SO4 3. So sulfate, of course, is SO4 3, or SO4 with a 2- charge, and I have 3 of them. So I have 3 of them. So I have a -2, -2, -2. So that's going to give me a total of -6, right? On the other side, that means I have to have a +6. And I have 2 chromiums. I don't know what the charge of it is. So I'll take my +6 charge, and I'm going to divide it by the fact that I have 2 chromiums, and that's going to give me Cr with a 3+ charge. And if that's the case, this is going to be chromium (3), Roman numeral 3, sulfate. That's kind of similar to our example. So let's go through some of these other ones. Go ahead and take a shot at questions 2, 3, and 4. I'll give you a minute or two to go ahead and come up with an answer. Once you feel like you have an answer to the ones that, once you feel like you have an answer that you can, or if you feel like you can't answer it, you can just raise your hand. So if either you get answers for each of those 3, or if you've done as many as you can and you just don't think that you can get answers for any of the rest of them, just go ahead and raise your hand and let us know you're done. That's the little raise hand guy. I just went ahead and put my little hand symbol up. It's in the bottom middle of the screen. You'll be able to see it. There's a little raise hand button. Just throw up that little raise hand button when you're ready.
Are we supposed to do it the way we did it previously?
Yeah, so yeah, just like the one that we just did with number 1. If it needs a Roman numeral, then you would include a Roman numeral. If it doesn't need a Roman numeral, then you don't have to include one. Interesting guess. So I got one person who's ready to shoot out some answers. Frank, go ahead.
Is the first one iron 3 carbonate?
It's a good guess, but it looks like you did the thing I told you not to do. It looks like you did. It looks like you did the reverse crisscross, right? You said you did this, didn't you?
I looked at the list you gave us for the 8 polyatomic ones we were supposed to do, so I probably shouldn't be relying on that much.
Mm-hmm. So what's the charge of carbonate? CO3. Yes.
2.
2. Yeah, the charge is 2, so we got a 2 minus here. And how many carbonates do we have?
1.
1. So we have 1 carbonate. And that means if the total charge is -2, that means iron must have a charge of what?
2.
2. Yeah, +2.
Yeah, +2.
No problem.
Is it +2 or 2 plus? Is it +2 or 2 plus?
Mm-hmm. That's a 2
2
plus. Now, actually, okay, so you bring up a good point. Somebody said, is it 2 plus or +2? And technically speaking, for some whatever weird reason, chemists always write the number first and then the symbol, 2 plus, instead of +2. Although your professor is really never going to ding you on that, so it doesn't really matter. But yeah, technically speaking, the quote-unquote proper way of doing it is to put the 2 first and then the plus sign. But yes, so iron is a 2 plus, so this would be iron. Iron Roman numeral 2. Exactly, iron Roman numeral 2 carbonate.
Oh, that's I feel the carbonate.
Now, what about number 3? I got a hand raised. Yes. Yes, Jesse?
CD2OH.
Oh, never mind. You already answered it.
Oh, I'm sorry. Do you want to take a stab at the next one? Okay, Jasmine, you want to take a stab at the cadmium?
I just had a question about like a
Sure.
simple way of figuring it out. Couldn't we just do the -2 times 3, get the answer for that, and then divide it by 2 or divide it by the 1?
Well, you can't because you don't actually have 3 carbonates. You only have 1 carbonate. See, this is where we have to be kind of a little bit careful because carbonate as a whole is CO3. You only have 1 of them. You don't have 3.
Oh, okay.
But that's a very good question. Thank you for asking it. 'Cause that can definitely be confusing. Okay, Linda, what do you think?
Is it CD2OH? That's cadmium hydroxide?
You're saying cadmium 2 hydroxide?
Yeah.
Well, actually, this is a trick question. You are correct that it's a +2 charge, but cadmium is one of those magic staircase elements. Uh-oh! Which means you don't actually need a Roman numeral.
Yeah, I didn't put a Roman numeral. I just said cadmium hydroxide.
Oh, okay. Well, then there you go. Good job. Look at me putting words in your mouth. All right. Yeah, no, cadmium hydroxide, absolutely. So this is one of the magic staircase elements, and therefore it does not get a Roman numeral because it always has the same charge. It's always a +2. All right, what about MnO2? Here's a fun one. What about MnO2? What do we get for that one?
Mn2 plus 0.
Nope.
No? Manganese, manganese oxide? Nah.
Not quite.
Ouch.
What's the charge of manganese? Anybody have an idea?
3 plus.
It's not a 3+. I think you're just guessing though.
The what? Is it negative?
Okay, so oxygen has a charge of what? I think Frank indicated it. I don't know if he was trying to indicate this charge of oxygen, but I think he was. Oxygen has a charge of 2 minus, right?
-2, you mean?
But there are 2 oxygens. So that means there's 2 minuses. That gives you a total charge of -4. Which means that the manganese has to be a charge of +4. So this is going to be manganese 4 oxide. Manganese 4 oxide. Manganese. Manganese 4 oxide. Yes.
Okay,
Go
so
ahead.
I just wanna make sure I understand this right. So because there were no parentheses to separate the compound, that makes it to where the 2 is for the entire thing, right?
Well, the 2 only refers to the atom or polyatomic ion that comes immediately before it. So if there's a parentheses, the 2 refers to the entire polyatomic ion. If it is if it's just an atom, if there's no parentheses, the 2 refers to the atom that comes immediately before it. What you have to look for, and I understand what you're saying. What you have to watch for is if there's more than 2 atoms. So in this case, there's only 2 different types of atoms, right? There's the manganese and the oxygen. In that case, you can feel confident that that means there's 2 oxygen ions. Whenever you have 3, notice you have 3 different elements here, iron, carbon, and oxygen. Whenever you have 3 or more elements, that means you almost certainly have a polyatomic ion. And if you have a polyatomic ion, that means you have to treat it as a charged molecule. So that CO3 is a charged molecule. It's
Okay.
not separate. Yeah. Does that help at all?
Yes, it did. Thank you.
You're welcome. Oh, I hear cute babies. Yes, Jesse?
So should that CO3 and the iron carbonate have parentheses around it?
It doesn't need to because there's only one of them. If there's more than one polyatomic ion, you must use parentheses. But if there's only one polyatomic ion,
Oh,
you don't use parentheses.
yes, okay. Thank you.
No problem. Awesome. Any questions? Does that make sense? All right, cool. Well, let's go ahead and take a look at the next. Let's go ahead and take a look at the next one. Look at covalent compounds. Now, fortunately, this is going to be a lot easier than ionic compounds. Because covalent compounds, we're only going to learn how to name binary covalent compounds. That's basically these little two atom compounds composed of only two different types of atoms. And because because covalent compounds are between nonmetals, because they're sharing electrons, they can share in a lot of different ways. And that means they don't have any particular charge or anything. They just share in different ways. So let me go ahead, actually, before I start going through some of these different rules, I want to kind of explain something here. Like, for example, if you just look at, for example, nitrogen and oxygen, well, you can have nitrogen with one oxygen. You can have nitrogen with two oxygens. You can have two nitrogens with one oxygen. That's called laughing gas or nitrous oxide. You can have two nitrogens with five oxygens. You can have two nitrogens with four oxygens. All of these are real compounds. All of these actually exist. There's no way to predict. There's no way to predict which one you're going to have. I mean, other than like knowing what the chemical stuff, the chemical properties are of these different things. But if somebody just says you have a compound with nitrogen and oxygen, you're not going to know what it is unless the formula is expressed to you. So you can't just say nitrogen oxide because I don't know if that's NO, NO2, N2O, N2O5, or whatever. So what we do for covalent compounds is we use prefixes to tell us how many of each atom there is. So it's really easy to name them. All you have to do is name the first element with a prefix, unless there's only one of them. Then you don't, unless the prefix is mono, you don't need to use the mono prefix for the first element. So, like in this case, nitrogen, I don't need to use the mono prefix for that. If I'm naming this one right here, I can just call the first element nitrogen. Okay? I don't have to say mononitrogen. But for the second element, I am going to give its appropriate prefix, but I do have to change the ending to IDE. So I use the same rule for changing the endings that I use with ionic compounds. I change the ending to IDE. Now, for the second element, if there's only one, like in this case with the NO, I am going to use the mono prefix. So this would be mono oxide or monoxide. So nitrogen monoxide. So I changed the ending to IDE for the second element. Does that make sense? Okay, let's look at some more examples. Actually, I'm going to go through a couple more examples first. So let's say we do this next one, the NO2. Well, once again, there's only one nitrogen, but it's the first element, so I'll just write it as nitrogen. Exactly, because it's two oxygens, I'm going to call it dioxide. Dioxide. Now let's skip ahead to, like, say, N2O5. For this one, now I have two nitrogens, So I am going to use a prefix for the nitrogen now. It's going to be dinitrogen.
Oh, I see. Pentoxide.
And then, yes, I'm going to use the second part of the name is going to be pentoxide.
Is it pentoxide or pentaoxide?
That's a good question. It's actually pentoxide. I don't know why this is the case, but for whatever reason, with oxygen, with the oxide, you'll drop the A's and you drop the O's of the prefixes. So like for example, and it's only with oxygen, none of the others. So penta, tetra, mono, hexa, hepta, octa. If any of those go with oxygen, you just drop the A. So decoxide. I'm sorry?
It might make a little bit logical sense because you have two vowels that will be clashing with each other.
Yes, but you want to know what's interesting? If you use tri or di with iodine, you still write it as triiodide. Like for example, triiodide. So it's not consistent. Like if it's iodine, you still write triiodide. You use the double vowel.
Okay.
It's only with oxygen that you don't use the double vowel. It's weird. I don't know why they do that. All right, let's go to some practice. All right, what's the name of this first one?
Carbon dioxide.
Carbon dioxide. Very good. You're familiar with that one. And well, we kind of already did this one. N2O5, that is dinitrogen pentoxide.
Yeah.
What about P4O10? What's that going to be?
Tetrapot. Is it tetrapot? Phosphorus.
Jesse, you want to go ahead? Do you have a question, or do you want to try and answer? Sorry, Linda. Let me get Jesse's question. Jesse.
I don't think I think I'm forgetting to take my hand down or something. Sorry.
Oh, no, it's no problem. Do you want to try and answer number 3? What do you think?
What would 10 be?
So P4. So the prefix would be.
I can't think of what the prefix is. I'm not sure.
Okay, so the prefix for 4 is tetra, and all those prefixes were on the previous page, so if you don't remember them, that's okay. I mean, you'll have to memorize them eventually, but yeah, so tetra, phosphorus, and then what's the prefix for 10? Deca. So it would be, so the whole name would be what? You got it. Yeah. Tetraphosphorus decoxide. You drop the A. For some reason, for some weird reason, we drop the A. We drop the double vowel when it comes to the oxide. So tetraphosphorus decoxide. Does that make sense?
Decoxide, right?
Mm-hmm. Sorry, I put you on the spot, Jesse. My apologies. All right. What about number 4? Anybody want to take a stab at that one?
Yeah.
Yes, indeed.
It's dinitrogen monoxide.
Dinitrogen monoxide. Very good. Dinitrogen monoxide. All right. What about the last one? PI3.
Phosphorus iod. Oh, hold on. 3 is what? 3 is
Yep.
triodide.
Yep. Good call. Yeah, phosphorus triiodide. Very good. Good job, Linda. There you go. Yeah. Dinitrogen monoxide, phosphorus triiodide. That's good. All right. So that's it. That's all we have to do with the writing and the naming of these different compounds. And what I would recommend, unfortunately, research has shown that it takes approximately repeating a particular task about 25 times to commit it to short-term memory, and takes roughly up to 75 times to commit it to long-term memory. So the best thing that you can do with this naming and writing stuff is practice, 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 practice. However, the good news is that have I got a deal for you? I have awesome practice problems for you to work on. Let me show you. So on our website under Chemistry 1406, the Chem 1406 practice problems, if you scroll down to compounds and their bonds, we have ionic formula practice with the answer key. And it has, you write the ions, you write the formula, gives you the names. So there's ionic formula practice 1, ionic formula practice 2. There's another 50 problems. You have naming ionic compounds, practice naming with also with the transition metals. You have mixed ionic and covalent naming and formulas, because that's the form you'll probably get it on a test. You'll probably be given it without it designating whether or not it's ionic or covalent. You'll have to figure out which one it is. So we got mixed ionic and covalent naming, and each one of these comes with its own answer key. So there is literally hundreds of examples here that you can use and practice with. Not that you want to do hundreds of problems, but I mean, like, you know, oh, how do you get there again? That's a good question. Let me go ahead and show you. Okay, so let me share my screen again. Show you. If you want to get to our website, easiest thing you can do is you can go to any search engine, but if you just type in TCC space SE space science, it'll pull up our TCC SE Science Learning Center Google site. And you can go straight to Chem Web Resources if you want, or you can go to the main site. Go to the main site, you can click on Chemistry Web Resources. And from there, you can scroll down to Introductory Chemistry or Chemistry 1406. That's going to have your chapter reviews, practice problems, practice tests, and video tutorials. The practice problems is where you're going to find all those practice problems on ionic and covalent naming and writing of formulas. And just scroll down to compounds and their bonds, and here they are. Yeah, no problem. Yes, Linda?
Yeah, were the videos made by you, or is just a random YouTube video?
Well, okay, so they're not random YouTube videos, but okay, I'll say that a few of the videos, there are videos that are made by me that are up on the website and everything. However, most of the videos are YouTube videos, but I actively hunted down what I felt to be the very, very best videos. And I actually searched and I looked through a lot of them and I screened them to make sure that there's no errors. And if there are multiple videos on a particular topic, I watched the different videos and I picked the one that I felt best explained the topic at the level you needed to know it. Because a lot of times the videos that you're going to come across on YouTube are either going to have errors in them, or they're going to be too advanced, or they're going to be too simple. And so I did the legwork of finding those videos that would most perfectly match your course. So even though they are YouTube videos, it's better than going straight to YouTube, because in this case, those videos are videos you can confidently look at and be like, okay, so this is what I need to know at the level I need to know it. And these are going to be good videos. I don't have to worry about terrible videos that don't make sense. Does that make sense?
Yes.
So it's a little bit better than that. Now, Jasmine asked a really good question. She said, where do you find this recording? Okay, so let me actually show that as well. Once again, it is up on our website. So it is up on our website. So going back to, let's see, you have the home TCC Science Learning Center. On the top top bar, there's a workshops and events section right here. If you click on there, you will also have, if you click on there, it'll have all the workshops. And if you click on the Chem 1406 ones, it'll have the video replays of the previous workshops we've done. So there's the significant figures workshop here. There's the conversion factors one we did here. And after we finish up with this one, I'm going to go ahead and edit it and post it up onto the website, and it'll be right below here. Does that answer your question?
I think so.
Yeah, no problem. Also, I should also note that if you, so let's see. I should also note in the email that I sent you with this, notice on the bottom it said missed our previous workshops. Check out the replays on our website, link provided below. If you click on that link, it'll take you directly to that page that shows the workshops. So it's also in your email, the email that I sent out to y'all. Thank you all for coming. Have a great day. We'll see you all next week. Bye-bye.